by Mr. Lee. He ran from Wuhan University. Wuhan from.
Good afternoon, everyone. My name is Lei. I'm a PhD student in Wuhan University in China. I also study in the University Complutense of Madrid. Today I will present our work on a sliding time window RBF network for the calculation of wind turbines using fast data. So let's start with the background. As we all know, the offshore wind energy is the fastest growing renewable sources globally, and also for the modern large-scale wind turbines, especially for those above 10 megawatts, the pitch control is more critical. As you can see from the wind turbine's power and wind speed curve, the wind speed between the cutting and the rotating speed, we just need to use the torque control to capture the maximum power output. But when the wind speed exceeds the rated wind speed, we have to use the pitch control to adjust the blade pitch angle to limit the power output as a rated power. And it can also help to reduce the structural loads on the wind turbines. Now the most widely used wind turbine simulator is a open fast from rail, and it integrates multiple dynamic modules. And but for the blade pitch control, it uses the scheduled PI collective pitch control, or the CPC. However, the native CPC controller of OpenFast has a limitation. It cannot be easily exported as a standalone module. That means it's hard to use it in the hardware user group and also for the rapid prototyping. So there is a clear need for a lightweight high-fidelity solid model to replicate the behaviors of the native OpenFast CPC controller. And the most existing work focuses on 2 points. The first one, designing the totally new pitch controllers with different methods. The second, optimizing the parameters of the PI controller. But both of them, we address the requirements on lightweight the deployments and also the no online training. So our objective is to build a lightweight high-fidelity solid model. Meets the three criteria. First, it can exactly replicate the input-output behavior of the OpenFast CPC controller. And the second, it can run fast enough for the real-time hardware loop simulation. And the third one can generalize well the unseen wind conditions. So our key idea is to combine the radio basis function network with a multi-scale time sliding window features. So here is the overall framework of our approach. It consists of 2 parts: the offline phase and the offline training and the online deployment. In the offline phase, we first generate the time series data from the OpenFast simulations using the DLC 1.1 showcase. Then we process this data with a sliding window to extract the 14-dimensional features. We construct the training data set where they encoded the features vector and they uploaded the next feature angle set point. We train the RBF neural network using the rate regression and tune all the capture parameters on the vibration side. In the online phase, we use a circular buffer to store the last 30 seconds of real-time sensor data. We compute the same 14 features, then feed them into the trained RBF model to get the pitch angle command, then send them to the pitch actuator to generate the final pitch angle. So the advantages of our framework are there's no online training. It's the fixed computational cost for each step, and it's easy to deploy. Now let's talk about the data generation and pre-processing part. We use the IEA 50 megawatt offshore wind turbine hardware study, and the data side comes from the IEC standard, the DLC 1.1 low pace, which corresponds to the normal and turbulent wind above the rated wind speed. We use the sliding window 30 seconds, we train a vibration head split follows the time series split to avoid the data leakage. Our point innovation here is our multi-scale features extraction. We extracted 14 features from the 5 base variables with 3 different window scales. The first one is the fine scale window from 0 to 2 seconds to capture the fastest transients, like the slope of the generator speed arrow. And the second one is the medium scale window from 6 to 15 seconds to capture the medium dynamics, like the integral of the power arrow. And the third one is a core scale window, 30 seconds, to capture the steady state trends, like the standard deviation of the wind speed. With this design, then it can meet the different time constants of the wind turbulence and the generator dynamics, also the pitch actuation. Now let's talk about why we chose an RBF neural network. We experimentally compared the RBF with the LSTM. As you know, the LSTM is the most widely used sequential model for time series prediction. But in our study, as you can see from this table, the RBF trains in just 50 seconds, while the LSTM takes more than 20 minutes. Also, the RBF has a fast inference speed, the excellent local approximation ability, which is crucial for the controller's applications. Also, it has a simple structures. It takes our 14 features as the input. The hidden layer has the 500 centers. The activation function is a Gaussian radial basis. It can measure the similarity between the feature input and each cluster center. And the output weight are solved in the closed form using the ridge regression, which has the L2 regularization to prevent real conditioning. Because no iterative back propagation is needed, so the training is so fast. All the hyperparameters are as follows, and all of these are systematically trained on the validation side. So now let's talk about the results. Starting with open loop prediction. Based on the independent data set of DLC 1.1, we achieved a great performance here. As you can see from the scatter plot, the predicted pitch angle aligned almost perfectly with the actual pitch across the full operating range from 2.8 to 24.5 degrees. And the extremely low differential ramp-seq is 0.08 degrees. And that means the prediction is really smooth, and also there is no high frequency in artifacts. That means it can help the actuator value. But the real strength of our model is not its generalization ability. Remember, we just trained our model on the DLC 1.1 locus. Then we tested it on the 2 completely unseen locuses, the DLC 1.3, which is the extreme turbulence, and the DLC 1.6, which is an extreme operating gust. Even on these harsh conditions, all the R squared are above 0.97, and the Pearson coefficient, correlation coefficients are above 0.99. Although the ramp-seq increased a little here, but it's just because of the extreme transients. And so this proves our model learns the intrinsic safety logic, not just memorize the specific wind pattern from the training data. And then we compared our RBF controller with the native open-fast CPC controller under the turbulent wind. And as you can see from the time series plots, the pitch angle of our RBF controller, it follows the same trend as the baseline. And for the mean value for the pitch angle, it differs If you're less than 0.5%, which is almost negligible, but most importantly, the standard deviation of the pitch angle. It has this lower, it has a lower value for our RBF controller. That means it can have a smoother pitch action, and also it can help reduce the actuator fatigue. For the generator speed and the power output, they are virtually identical to the baseline. So there is no baseline. So in summary, our RBF controller replicates the behavior of the open source PS sharing schedule controller with a high fidelity and no stability issues. So to conclude, we successfully emulated the open source CPC controller using the RBF network, combining the sliding window features. We achieved a high accuracy in both the open loop and the closed loop tests. They can generalize well even to the unseen extreme swing conditions. It's lightweight, fast, and portable. It's suitable for the different environments. In our future work, we will extend it to the individual pitch control using the RBF network. Also, we can consider it to integrate it with the reinforcement learning or fuzzy logic to enhance the performance of the controller. So that's all. Thank you for listening. I welcome your questions.
Anyone has a question?
So there are many control schemes and also algorithms. So maybe have you made any comparison with your method and other methods in the literature? That can be very good also for the extended paper. Just to put a comparison table.
Yes.
And look for the, let's say, the time of the response and so on. And can you make a kind of comment on that? I mean, just a comparison between the literature and your work right now, or maybe?
Yes, we are planning to do that. Compare it with more controllers and also use a reinforcement learning to also improve the performance. So that's it. Thank you.
There are questions? Other questions from the present? Thank you once again for your presentation. Moving now at the second presentation. The title is Performance Analysis of Machine Learning Models for Instrumental Multi-State Sharp Estimation. It will be presented by Mr. German from Istanbul Technical University. Please welcome our second presenting speaker.
that, my name is Enes Edilgün. I'm an undergrad student from Istanbul Technical University, and today I will present our work on the performance analysis of machine learning models for lithium-ion battery state of charge estimation. All right, why state of charge matters? Basically, the state of charge is battery's fuel gauge. That's the percent of the usable charge remaining. But unlike a fuel tank, you cannot measure it directly. You can only measure the voltage, current, the temperature, and then try to make an estimation out of that. And about that matter, the stakes are high. A good estimation protects the cell from overcharging. Prevents overcharge, deep charge and thermal risks, also maximizes usable range and grid storage dispatch, reduces the stress cycle that accelerates aging. Every electric vehicle and every grid storage system depends on its battery management system, in short BMS. And that roughly targets the state of charge accuracy around 1 to 2%, give or take, only by using the three signals that we mentioned before. In the classical estimation, there are three main families: common counting, which integrates current but drifts as errors accumulate; equivalent circuit models, which are simple but hypersensitive to their parameters; and common filter observers, which are accurate but depend on an accurate physical model and careful tuning. They share one crucial weakness. They will assume that you have a good physical model of the battery. And in the real world, that assumption, of course, breaks, and that causes some errors. And the naturality of the lithium-ion cells are strongly nonlinear. The nonlinearity shifts with temperature, with aging, and also hysteresis. This is exactly what pushes us towards a data-driven approach, rather than model the physical battery and learn the behavior directly from measurements. We made some contributions on the battery. First of all, a field name independent extraction framework that scales across massive data sets. We managed to do that. Second, a sliding window feature construction that lets standard regressors learn temporal dynamics. And the third one, a multi-metric evaluation, because as you'll see, a single headline number can be misleading. We also used 5 different models for the comparison. I will get on that later. All right, the data set being used was Panasonic's, a single lithium-ion cell looked under diverse drive cycles and temperature in MATLAB format. Our inputs are voltage, current, and temperature, as you can see. And of course, the target is the state of charge. In public data sets, signal names vary across files. There are multiple files, and sometimes the signal sits inside a nested struct paths. A loader with hard-coded names, that's why the hard-coded names slightly failed. As I mentioned before, that's why we did not hard-code them, but made a little model that can understand which data is which. We deliberately used real drive cycle data across varying temperatures, not just lab-generated clean data. That's why the signals are dynamic and the estimation is genuinely hard. It mirrors what a battery actually experiences in a vehicle and in real-life situations. The pipeline, here's the full pipeline. First of all, as I mentioned, auto signal extraction detects the state of charge from the nested structs. Then we use this slide window feature for construction, a Z-score clip for normalization and cleaning, training the selected machine learning models, and then the evaluation. For each model, an identical data set is used for better comparison standards, and we will see the performances a little bit later. This is basically the heart of the method. The key idea on that is sliding window construct is one instant of the signals is not enough for the state of charge, because state of charge highlights the total recent history. So for each step, we stack the previous window samples for all three signals into one flat feature record. The label is the stable charge at the end of the window, and we can say why does this matter? Because the window embeds temporal dependency directly into the feature space, which means ordinary regressors can learn better dynamics without a recurrent neural network. And the correlation matrix on the right conforms temporally adjacent. Features are strongly correlated, decaying with time distance exactly as we hoped. These are the machine learning models that we have chosen. The linear regressor, a fast baseline that can capture we cannot capture nonlinearity. A support vector regressor, kernel-based, robust to noise, but scales quickly. A single decision tree, flexible but prone to overfitting. Then two assembly models, random forest, which averages many trees, and gradient boosting, which builds a tree sequentially, each one correcting the previous error. The question is that, does the added capacity actually pay off? And the answer is yes, it does. Linear regressor is visibly deviates in nonlinear regions, while the decision tree tracks better but introduces small step discontinuities. And the assembly, the random forest, and the gradient boosting hug the reference curve most correctly, capturing nonlinear battery behavior exactly we hoped. If we check out the error distribution and the consistency, on the left here, we can see that the assembly models errors are slightly more accumulated on the zero region, and on the right, the cumulative error curves, gradient boost and random forest rise fast, as you can see here. Meaning more of their predictions forward to small error ones. Support vector machine, the vector regressor, shifts right, carrying large deviations. And error zero center errors means threshold estimations, and the gradient boost is the tightest in that manner. Here's the full metric and performance metric comparison. We can see that gradient boost achieves the lowest RMSE and the lowest MAE. Actually, for whole the performance metric, it's in a better case. So we should say that why we use that much of that many performance metrics, because as the data doesn't change much in the data set, we have to check not only for the R-square and other metrics too. And as you can see, gradient boosts wins in this fight. All right, and why does it win? Non-linearity is the deciding factor in that matter. Bagging tames variance, which makes random forest stable, and boosting attacks the residual directly, which gives gradient boosting its edge. All right, so where does this sit in the real system? Right in the middle, actually, between the sensors and the EMS control, because it's battery model free. It retains from data and the pack changes. Inference is fast enough for embedding hardware, and tighter state of charge bonds let the power electronics operate closer to the limit safe. All right, to conclude, our automatic extraction made the pipeline scalable. The sliding window lets standard regressor learn dynamic without a recurring network, and gradient boosting lets on every metric. The clear message is that for practical, reliable state of charge estimations, assembly learning outperforms single learners in the combat. So, our next step, the hyperparameter tuning part of the project. Also, we will take this project as the baseline and make a comparison with the LSTM and CNN. So to figure out if we really did that would work on feeding the regression models. And also, I would like to say the acknowledgements. Thanks so much to my dear teacher, Dr. Girgin, my co-authors, and of course, Istanbul Technical University. Thank you so much for listening. If you want to ask any questions, I can take them now, and also you can scan the QR code. It's linked to my LinkedIn. You can ask any other questions or any collaboration requests at any time of the day. Thank you.
Thank you again for your presentation. Moving now to the question, one or two questions. Yeah.
Yeah, there are many different machine learning models right now.
There are.
I mean, all over the world, they use for, I mean, many different areas. So actually, which models you used, and can you make, for instance, a few different models, and can you make a comparison among them for the extended paper also? That can be a very valuable contribution.
Of course.
So maybe you can make a comment on these comparative cases.
As I showed previously, in this current project, we already have 5 models. So we will choose the best one, ready who's machine learning model. And for the later works, we are planning on comparison them with CNN or LSTMs, maybe another neural network. We didn't choose it right now, but we are planning on it.
Mm-hmm.
So if the question is, why did you choose these ones? And then the answer changes a little because the technology is improving really fast, and always we say that there are neural networks, there is AI and things like that, but there may be a simpler solution and better computational costs in the areas that we did not check. So here we are actually trying to prove that with a little bit basic ones.
Mm-hmm.
All the techniques that we used, they're all supervised learning techniques. Whatever the ML techniques you have used, they're all supervised learning in the product category.
Yeah.
Did you do it because of you had a limited data set?
It's not because of the data set, but this is part of the big pushing. We just thought that we checked the data set with statistics, right? And so that the assembly methods and models that can be comparable to them can be enough. So that's why these models were chosen.
So generally, we apply, we have a small data set, we go to like learning, the number,
Yeah.
and then we can also like update the data. We can create more data set within the statistical framework, and then look for the neural network.
That can be the next step.
Foto.
Now moving to my presentation. It's It's my pleasure to present to you our work entitled Robust Hybrid Stochastic Optimization Approach for HPPC Enhancements and Energy Management in PV System with Hybrid Storage. The presentation outline is structured as follows. After introduction, we proceed to background problem and motivation. Then the methodology, followed by optimization algorithm and energy management. And before conclusion, we present some simulation results. The increasing demand for clean and renewable energy has accelerated for deployment of PV systems worldwide. However, PV systems are non-linear and their performance strongly depends on solar irradiance and temperature. Conventional MPPT are not often fail to maintain optimal operation under dynamic weather conditions because of their slow convergence and limited tracking capability. Therefore, developing a fast and robust optimization strategy remains an important research challenge. The primary objective of this work is to maximize the power extracted from PV system while ensuring stable energy management. Our main contribution is the development of an enhanced gray wolf optimizer incorporating a Gaussian initiation operator in addition, we integrate a hybrid energy storage system composed of a lithium-ion battery and supercapacitor to improve power sharing and system reliability. Finally, the proposed approach algorithm is validated through comparison with several well-known algorithm optimization. Let's move to system configuration and modeling. The PV array, this slide illustrates the proposed PV array system. The PV array is connected to DC load via DC-DC boost converter, this converter is controlled by the proposed algorithm, and the produced energy is stored in the both battery and supercapacitor. The stored energy is controlled by back boost converter with this management energy strategy. Let's move to configuration and modeling. Here, the slide briefly presents the mathematical models of the PV, the battery, and supercapacitor in the proposed system. We can now formulate the optimization parameter and constraints. The objective of optimization is to maximize the power from PV system by adjusting the converter DC cycle. Several constraints and of optimization incorporating the DC cycle limits, DC bus voltage stability, and while maintaining power balance between battery power and supercapacitor. The gray wolf, let's move to optimization algorithms, starting with conventional one, gray wolf optimizer, GWO, is a nature-inspired mineralistic algorithm based on the hunting behavior of the gray wolf. The research or the search process is guided by the tree-based candidate solution known as alpha, beta, and delta wolf. the mechanism provide a good balance between global exploration and local exploitation. The flow charts here summarize the main step of the convolutional gray wolf optimism. The algorithm evaluates the continuous solution and updates the provision until the optimal operation. Moving now at the second or our contribution is about Bushy-Gaussian gray wolf optimism, named CGGWO. Our main contribution of this work, we enhance the convolutional gray wolf optimism by introducing a Gaussian mutation operator together with a greedy selection strategy. These improvements increase population diversity, accelerate the convergence, and reduce the risk of premature convergence. As a result, the proposed algorithm achieves faster and more accurate maximum power points taken under dynamic environmental conditions. In the next section, I will present the proposed energy management strategy and the multi-loop PE controller. This flowchart resumes the main step of the proposed algorithm, CGGWO, the main step. The slide presents the proposed energy management strategy combining a battery and supercapacitor for intelligent power sharing dynamic. Dynamic MPPT algorithm selection is here, and battery protection through automatic DC bus voltage regulation at full charge to protect the battery. And multi-loop PE control are used. Three loops, two currents, two for currents, battery and supercapacitor, plus one for DC bus voltage. The principle, low frequency battery and high frequency supercapacitor decoupling. Now let's move on simulation results. The slides presents the validation of PV array, the battery and supercapacitor models. The simulation response closely match the expected electrical behavior under dynamic condition. With these models validated, let's move to dynamic scenarios, functional validation. With 5 operating phases, simulate variation in solar, irradiation, and load demand. This result demonstrates a stable DC bus voltage, intelligent power sharing, and fast adaptation to changing operating conditions. When the battery rush 28% of state of charge, the control strategy automatically switches from MPPT to DC bus voltage regulation, with the PV system supplying the load directly. As the battery SOS state of charge decrease, the controller returns to MPPT algorithm. Having validated the functional of system, let's move to the simulation results by integrating the algorithm optimization. This slide compares the proposed CGGWO, the proposed algorithm, with conventional MPPT techniques, including perceive and observe, PSO, ASO, and conventional GWO. As observer, the proposed algorithm rushes the maximum power points more rapidly while significantly reducing oscillation around the MPPT point. Let's move let's move to compare the low power performance with the conventional known method, showing that the proposed CGGWO algorithm provides the best stability while maintaining adaptation to radius changes compared with other algorithms. The slide compares the DC bus voltage regulation performance, showing that the CGGWO and PSO maintain a desired value of voltage, while perceive and observe and conventional GWO exhibits large voltage fluctuation. The table summarizes the overall performance of the compared algorithm, highlighting the superior efficiency, accuracy, and dynamic response of the proposed CGWO algorithm. And finally, let me conclude with the main finding and future work. In conclusion, the proposed CGWO outperformed existing MPPT method by providing faster convergence, higher tracking efficiency, and more stable energy management than existing method. Future work will focus on real-time experimental validation. And thank you for your attention. Please, if you have a question, I'm ready to respond.
I have a question.
Yeah?
Since you use converter systems, the load time, I mean, is it active load or it also have some reactive load times?
Can you repeat
For instance,
from formulation?
Is it ohmic load or it includes ohmic load plus inductive or capacitive load?
No, it's just load, connected to load, PV system connected to load, not integrated to grid. With the storage system.
But the load type can be ohmic, only ohmic, or ohmic and plus capacitive or inductive.
Not just ohmic.
Just ohmic, okay.
Yeah.
So
Just
in
ohmic.
that case, for further,
Yeah,
I
it's
mean,
future work. Yeah.
I suggest
we can
to
add
add
yeah,
other,
and Dixit and
because
plus
in,
ohmic.
yeah, in reality, we have all this type of loads, and that can affect your results and also efficiency. That's very important.
For compare the proposed methodology, it's a good idea. Thank you. Another question? So I return to chairman. The third. Can I too? Yeah.
So that's like that. So the last
The last
talk.
moving to the last one. Now we move to the last final presentation of this session. The presentation is entitled AI driving predictive maintenance and power optimization strategy for distributed low power systems. It will be presented by Mr. Chantal Weber from Engineer Minor GmbH. Please welcome our final speaker.
Hi everyone, I'm Sedat. I'm the head of software of Miner, and we are here with Chantel. She's our CTO. And today's subject is software and AI-driven predictive maintenance and power optimization for distributed hydrokinetic energy systems. So yeah, we'll focus to the predictive maintenance and power optimization. So first, what are hydrokinetic energy systems? So it's basically an energy system that plays into the river, and the main source is coming from the flow of the water, and the current applies to the water, and the power is there. And for this system, the energy fish that we used for the test bed for our study is not needing any dams or reservoir or any infrastructure for producing electricity. That's our product as Energy Miner. So yeah, that's the main product that we use, the software and AI systems. So the biggest advantage of this device is installed in the river, which is producing electricity 24/7. So it's not like it's better than the comparison with the wind and solar. And the reason that we studied about this topic is the production time. So we are producing the electricity for 24 hours, so that means we need to have a better optimized system with a loss failures. So these are, so let me introduce some technical detail. So the energy fish is a device, a small device in the kilowatt sizes, so that means we need the fleet of it. So some advantages or like the profits that we can make as a small percentages can make a lot of improvements for the total like bigger picture. And yeah, you can see the overview of the location in the river, but yeah, that's the installation sites for the river site. And our main topic related to the energy fish is the data. And this is the data life cycle on here. So first we have the hydroelectric fleet that is sending the data via canvas with 3 Hz. And then we have our core compute model, and we are buffering the cloud system with the data packages after doing some modeling inside of the compute model. And yeah, so we have all these data, and what can we do with the data? We can basically improve the efficiency. So the system efficiency is the key part in here because, as I said, it's the kilowatt size devices, and all the profits that we can make a bigger impact in total. So we have 2 main topics. The first is the reduced events that cause loss of power, which means the failure scenarios that we have. And for reducing the events, we need to have the predictive maintenance model for predicting the failures beforehand. And then we need to avoid those events. And the second one is increasing the normal operation efficiency, which is, we will go in detail with the operation modes. And yeah, that's the 2 main topic. So the method 1, the predictive maintenance pipeline is working more or less like this. So we have the sensor data that first as a raw signal data, the RPM, torque, current, voltage, and power, and they all have some relation between each other. So they are consecutive data, and then we have our prediction model. But how can we predict the failure without knowing the pattern? So that's why first we need to have the fault detection to predict, to be able to understand what's going on in the system. So first we need to create the scenarios for the failures, and then we're able to understand if there's a failure or not. Because if we are not sure about the failure's characteristics, we cannot identify them as a failure. And then we have several flags for early warning before the failure happens. That's what the predictive maintenance comes to the table. So we are predicting the failure. We are not detecting the failure anymore. We are predicting that failure is coming, that's why the controller reacts. So the continuous monitoring is the reason for the reaction. Because if it's not a continuous monitoring, you cannot react to the failure and you cannot prevent that failure. So yeah, that's the first one. And the main question after this period is, can we trust the model? Is that a black box, or how can we understand we actually did something? And here's the explainable AI is coming to the topic right now. It's the shock interpretation, so it explains the relation of the variables or the ratios to the failure scenarios, basically. And we can see that T-1 RPM is the most sampled one, but our key focus is torque to power ratio, because in that ratio you can understand that you have something going on without producing any power. So that means there's a power loss, and yeah, this is the explainable AI part. And yeah, the second method is the MPPT that we were running on the device, the operation mode. So as you can see from the graph, there is some sweet spot, but it's really hard to obtain that exact spot. And because if you do too much, then you can go to zero rapidly, or maybe you can lose the power in between if you set the parameters incorrectly. And since it's a 724 running device, it should be structured really well and clean, let's say. And that's the second part. That's where the power optimization is coming to the slides, and the results as well. So the results for each topics are represented in this graph. So the good thing about this graph is these two topics usually against each other. Like, if you want to force some stuff and produce more power, usually you will get more failure. But in this two-phase study, at the first one, the interruption rate, the predictive maintenance stuff is reducing the failure with 5.7 times. And the second part is increasing the power utilization, like power production by 17%. And that makes this study powerful, because it's increasing the power output, but at the same time it's decreasing the failure rate, and at the end it will have better maintenance. And yeah, the two ideas, one turbine and real gains. So yeah, that was it. Thank you.
Excellent presentation. One question or two? Question? Yeah?
Actually, from the electrical point of view, I wonder what is the impedance of this device? Because the inner impedance value directly dominates the power you get from the system. Because when the load you attach at the output differs than the inner impedance of this device, then your power really externally gets lower value. So a kind of balance should be kept. Maybe.
So I can explain in detail what's going on here. So first, after the device is on the water, it gets some kinetic energy with the spin rate from the flow. And then we're applying current to break the water, like the kinetic energy, and produce the power basically. And in here, the predictive maintenance part is focusing to the ratio. So it's not focusing to the exact variables with the health ranges. So it focuses on the ratio to be able to understand the failure. So if you put the device into different water, it will be the same ratio, but the values will be higher, or maybe it can be lower. So the point of view for the study is just the ratio,
So
not the values itself.
for the electrical point, did you use inductive?
So this is the first part of the device, and we also have different parts into the previous side that is doing the other study for fitting into the grid. So this study is only for the yeah.
So, one question, question. Another question?
I've got a mischievous question. Tethers and devices and oceans.
What?
So you have a tether, you have a wire rope cable. How do you address the multiple issues of having wire rope cables across an ocean? So fishing, shipping, submarines, other
Yeah,
devices.
that's the different point of view. This study is only for the software and the optimization part. It's but there is the fish studies going on at the university.
Does your co-author have a response?
Yeah.
So these energy fish are actually only designed for river installations, so not sea installations. That's why it's about the size of a small car.
Okay, so for example, in the Rhone or the Rhine,
Yes.
you
so
still have subsurface issues.
Yes. So we have part of the approval process is always ensuring that you're outside of any zones of harm. So for instance, in the Rhine, we have an installation where it's flowing 124 of these by the end of the year, and there we also out of the main channel where the ships go. So typically you can, because we are so
So
small,
you say your zonal.
we choose the
I
zones.
understand. Very good, thank you.
Thank you once
Yeah.
again for the presentation. This information concludes the session. Thank you for your attention.
So I would like to ask, is Associate Dr. Jamal Hassan is here? And then this Jamal Hassan is here?
Yeah.
Yeah.
That's your
Okay. So, Aykerim, you are the only one who will be session chairman.
Yeah.
Because Sana wrote us that Sana Hungary, her flight has been very late. So tomorrow she will present. So therefore, you are the session chairman. Dr. Jamal Hassan is not here, I think. So you can just start from your talk. So in this session, we have only one talk. So actually, maybe I can make a reminder for this presentation. I have also supervised her. She's from Kazakhstan. Last a few years before, we have made PhD study in my lab. So she has improved herself, and she also made other experiments, and also they have put a new laboratory in Kazakhstan. So she works on energy harvesters, mostly inductive electromagnetic ones. So please, you can
Thank you. Good afternoon, everyone. My name is Aykerim Ismailova. I'm from Karabakh University, Almaty, Kazakhstan. Today I would like to present our work on the nonlinear dynamics of the magnetically levitated electromagnetic vibration energy harvester. In the study, we investigation how the excitation conditions improve the dynamic response and the output performance of the harvester. While we working magnetically levitated energy harvester, because harvesters have attracted considerable attention in recent years, because they offer several applications over conventional spring-based designs. Instead of mechanical spring, they use magnetic levitation and provide the restoring force. As a result, friction and mechanical wear are significantly reduced, and the impacts between moving parts are eliminated. In addition, magnetic levitation introduces non-linear restoring forces, making the system highly interesting from the viewpoint of non-linear dynamics. Research gap. Although many studies have been published on magnetically levitated energy harvesters, some important issues remain insufficiently understood. In practical, limited attention has been paid to the influence of initial conditions and the excitation history on the dynamic response of this system. Moreover, most experimental studies are carried out under harmonic excitation, whereas real environmental vibrations are usually very variable, non-stationary, and stochastic. Therefore, the objectives of this work was to experimentally investigate how the excitation conditions influence the dynamic response of the magnetically levitated electromagnetic vibration energy harvester. This slide shows the energy harvester investigation in our work, and this show base parameter, our prototype. The operating principle is straightforward. When the device is subject to external vibration, the levitated magnetic oscillate relative to the coil. The change in magnetic flux induces on electrical voltage in the coil. The non-linear magnetic restoring force makes this system an excellent platform for studying non-linear dynamics effects. Second slide, experimental setup. They evaluated the performance of the harvester, and experimental setup was assembled. The prototype was mounted on an electrodynamic shaker. The excitation frequency was varied from 2 to 48 Hz. The acceleration level was maintained at 1 G. Load resistance 1148 ohms. The output voltage was recorded using a data exclusion systems. This experimental methodology, the experiments consisted of two measurement series. In the first series, the excitation frequency was gradually increasing from 2 to 48 Hz. In the second series, the frequency was gradually decreased over the same range. At each frequency measurement were taken only after the steady state response had been reached. It is important to note that all experimental conditions remain exactly the same. The only difference between the two experiments was the frequency sweep this direction. This always us to investigate the influence of excitation history on the system response. This slide shows the main experimental results. During the sweep-up experimental, the resonance frequency was observed at 24 Hz, and the maximum output voltage reached 59 millivolts. During the sweep-down experiment, the resonance frequency shifted to 20 Hz, while the maximum voltage decreased to 28 millivolts. And a similar reduction was observed in both the output power and the output density. In conclusion, the experimental results show that the output characteristics of a magnetically levitated electromagnetic energy harvester strongly depend on the excitation conditions. We found that not only the excitation frequency but also the sweep direction significantly affects the resonance behavior of the system. The result also indicated that the system response depends on the excitation history and the initial conditions were to its non-linear magnetic integrations. Therefore, these effects should be taken into account when evaluating the performance of magnetically levitated energy harvesters, especially for application involving variable and stochastic vibration environment. That's all.
So maybe questions, we can get questions.
Maybe for the future study, we can also look for the different loads.
Different loads,
Yeah, because as I see from your slides, only one
One
load
load,
have
yeah.
used, but for other loads we can also.
Okay.
That's possible. Any questions? Okay. So thank you very much. We can make a photo.
Is Kazakhstan and Turkey?
So, Professor,
Put your laptop down and come with me in the presentation. Put your laptop down and come with me. I don't know if it's a Yes, you have. Come. Well done. Thank you very much.
Can I invite Goran Strabak forward? We have had a great day, actually. It's an intimate conference. As I said, we are going to get to know each other. We are dealing with important topics. Energy, we all know, it's our subject, it's important. We misfire on it. So we understand energy, but we're not so good at persuading people, politicians, communities, societies to adopt the good solutions. Even my question about the wire tether, they have a solution. And of course it will force the bad boats you don't want into the centre so you can observe them. So there are unintended good attributes of some of our concepts. Here in the UK, we understand stuff, but we can't manage ourselves. We have ended up with a terribly inefficient management system, which means our energy costs are 10 times what they are in our European neighbours. So we're a good university, we're rubbish managers. Goran today presented an opportunity for cooperation, and it is erudite, but he's got 50,000 citations. This is a man who knows his stuff. So we wanted to make sure he got a proper plug. So Goran, thank you for giving us that.
Very happy that we interact a bit and discuss some of these issues.
And thank you for keeping on popping back. It's great to have you. Ladies and gentlemen, that's the close of today's conference.
yes.
We are back on for the IC-MECI conference tomorrow at 9 AM. So those involved, please come back. It's a sort of half-day conference, so we run from 9 till lunchtime. There is a lunch, and you can sit down now.
Breakfast?
There's no breakfast. You can have breakfast in the coffee bar. And then we have the gala dinner. Houndsditch is just 4 miles from here, 4.3 miles. And you can take the district line along to Tower Bridge, and then it's about half a kilometre to walk. So it's all easy.
And also, we will also make group photo there.
Okay.
In the gala dinner. Yeah, just.
So, so we're going to have a good day tomorrow.
What time? The dinner?
6:00.
6:30.
Anyway, any other notices?
Nothing. Just after the presentations, my mission will continue because I will deal with your papers. I mean, for journals and editor-in-chiefs of journals, as you know. So that, my work always continues. So we would like to publish all of these good works in different journals, actually. So, but I am happy. For many years, we are working on that and to make scientific applications and to give educational and also academic contribution to the work. So we are trying to do our best. Thank you very much for your contributions. And in 2 weeks, we will make the topical selections for the journals with my other colleagues, of course, Peter and other colleagues. And then we will inform you from the CMT, I mean the paper submission website, and also with emails, and also from the website that what I expect from you. Just try to make much more contribution to the short form of your paper. So that's very important. I mean, just put some other results, much more detailed discussions, and improve literature part. Yeah, because when you start to explore a topic, you should always look at what the other people did before, because this is the scientific way. I mean, without literature, you cannot improve. Maybe you have recognized in some presentations that I have made some comments on comparative tables, comparison about the earlier studies and so on. These are very valuable because science indeed is not the thing only we did, but it is a kind of building that it gets from the many, many ancient times and before even ancient times, and we built a building which has interdisciplinary and very active and also changes very fast. So therefore, maybe you recognize we do not use I when we are writing a paper. So it means that even with only one author in the paper, we always say me. So that's the meaning that respectful to our earlier scientists, researchers, and so on, yeah, and also going to much more future with lots of other valuable contributions. It's a kind of respectful manner in that case. So therefore, I'm very happy to be such a very good institution, having good scientific past and also of that feature. And we would like to make cooperation for the next years also with our colleagues here and all other colleagues, because I'm always saying that we do not localize the conference. I mean, for instance, we did this conference here in London this year. Next year, we will have another city, another country. So we are open to all suggestions. We can evaluate and we can have much more, contribution to the scientific
community. So that's our aim. And we will discuss, we will try to find better solutions for the humanity and for our country, and because this is the improvement of the humanity that having such knowledge, data, that's the way of living also. Without data, we cannot live. Thank you very much. Please also follow the online discussions, because we will have also on the the third day of the conference, we will have the online presentations. There are very, very good presentations, and some of them, authors, they could not get visa, yeah, I'm respectful because every country has, his own rules, so we cannot discuss this. But in that case, they would like to make the contribution in online presentation. So we hope that we can also, we already sent the links, Zoom links to you, and then please try to follow also online presentations. Thank you very much for all your contributions, and hope to see you in Calabria.
Maybe I think you will. Maybe I think you will. 9 o'clock till 1 o'clock.